We have an example problem here. We have a circuit. In this circuit, it tells us the ammeter shown in the figure reads 2 amps. Find the EMF of the bottom battery. So in the circuit, the ammeter is represented as the A with a circle. An ammeter, think amps, it measures the current flowing through it, which it's telling us 2 amps. We are assuming an ideal ammeter, meaning the ammeter itself has no resistance, so that there's no voltage drop across it. Now, we have 2 batteries in this circuit. The top one is 15 volts. This bottom one is what we are looking for. That's what we want. Hopefully you remember the long line of the battery represents the high potential end. The short line represents the low potential end. Whenever we have multiple batteries, when they're not in the same line, we have to use Kirchhoff's rules or laws. So we need to write an equation representing the junction law, an equation representing loop laws. And we typically need 2 loop laws and then the 1 junction law. Notice in the picture, they have already drawn I1 and I2 for us. That means we need to use the direction they've drawn. Since they've drawn I1 coming down on the left, that means that current is coming out of the positive end of that battery. It's also going into the negative end on the other side. They're only showing us the value at one point in the circuit, but it had to have come from above. Similarly, the I2 that is drawn here had to have come out of the negative end, the positive end of that bottom battery, which means it would have flowed into the negative end. With the directions they've given us for I1 and I2, they're both flowing towards this junction right here. So that means the current that flows through the middle has to flow to the right. We can't have all the currents flowing into the junction because that would imply they then stop, which of course is not going to happen. So our junction law equation, we have I1 and I2 already drawn for us in the picture. They're both drawn pointing towards this junction right here. So those would represent the currents coming in. They must add up to equal the current going out, which would be I3, which I know. I'm going to put 2 for my 2 amps so that I remember that this is a value that I have been given. Okay, so junction law is always currents. Currents into a junction have to add up to equal currents out of the junction. Now we need loop laws, equations describing the summation of delta V's as we go around a circuit. Okay, I don't know I1, I don't know I2, and I don't know that bottom battery voltage. So these are all unknown. If I have 3 unknowns, I need 3 equations. I do happen to know, though, or I can figure out, delta V for this 5 ohm resistor will be this current flowing through it, the 2 amps, times its resistance. So I do know that delta V is 10 volts for this 5 ohm resistor. So if I can take a loop that will take me through that 5 ohm resistor, then it will probably simplify an equation down a little bit. So for example, the top loop. Top loop. I'm going to call this 7 ohm resistor. I'm going to say it has a delta V1, or let's just be consistent to the last one. A delta V7, meaning the 7 ohm resistor. This 2 ohm, I'll call it a delta V2 for the 2 ohm resistor. Top loop, I just need to choose somewhere to start. I tend to like starting in corners somewhere, though you don't have to. If I start here, it doesn't matter if I go with the current or opposite the current. I just have to make sure I end up here as well. If I do go with the current, if my path takes me with the current, this first thing I'm going to pass by is the battery, and the last thing I'm going to see is the positive sign. So I'm going to see an increase of potential of, I'm going to just call this an epsilon 1. I'm going to set it up symbolically, and then we'll plug numbers into it. As I continue going, I'm moving with the current. Current flows high potential to low. So if my path takes me with the current, I'm going to see a drop of whatever voltage is across that 7 ohm resistor. My path, I keep going. I want to go through the middle here. So as I go through the middle, I'm going with the current. Current flows high to low. So if I'm moving with the current on my path, I'm going to see a drop of delta V across that 5 ohm resistor, which I know, I'm going to plug that in just a sec. I keep going around. The ammeter we're assuming has no resistance, so it will not have a delta V. We're back to where we started, so we can now say this equals 0. So let's go ahead and put in the values we know. So battery 1, EMF 1 is 15 volts. Delta V7, the voltage across this resistor depends upon the current flowing through it, which has been labeled a I1 times its resistance. Now, I1 is not 2 amps. That was in the middle branch. So for delta V, for the 7 ohm resistor, I need the current flowing through it times its resistance. So 7I1. Delta V5, we do know the current flowing through the 5 ohm resistor is 2 amps. Its resistance is 5. So we know there's 10 volts here. That gets us back to where we started. So that needs to equal 0. So let's see, 5 is equal to 7I1. So I1 is 5/7 amps. .714 amps. Awesome. We have I1. That's not what we ultimately want. We want the battery voltage. The battery voltage is going to come from looking at a loop that takes us through this bottom branch. So either the bottom loop or the whole outside loop. It doesn't matter which one. The bottom loop is maybe a tiny bit simpler, I guess. Bottom loop. We're looking at delta V's. We have to start and end at the same location. Let's go ahead and go up again first. So my path that I'm taking to finish my loop. The first thing I come to is this 5 ohm resistor. Because I'm moving opposite the current, I'm going to see an increase of delta V across that 5 ohm resistor. As I continue down here and go through this 2 ohm resistor, my path is taking me opposite the current. And again, current flows high to low. So if my path takes me opposite the current, I need to add the potential difference across that resistor. I keep going. The next thing I pass by is this battery voltage. The last plate I see, because I went high to low, so I'm going to subtract that battery voltage. That gets me back to where I started. So I'm now ending in the same location. So I make this a full equation by setting it equal to 0. Now plugging in this 5 ohm resistor, we already know we have 10 volts. Delta V2 is the current flowing through this resistor, which is labeled as I2, times its resistance. So we get 2I2, but we don't know the value of I2 yet. And I'm going to go ahead and bring the battery voltage to the other side. That's ultimately what we're looking for. So I need to know the value of I2 to plug in here to solve for the battery voltage. We have figured out I1. Now notice our junction rule, I1 and I2 had to add up to be 2 amps. So I2 is going to be 2 amps minus I1. So 2 minus the 0.714, I2 is going to be 1.28. I kept the whole digits that are in my calculator beyond the 4, the 0.714. So 1.2857. I'm not rounding too much yet because I'm not at a final answer. I can now plug this in for I2. Oops. I will round once I get this, since this is my final answer. All the numbers that were given to me were in 3 significant figures. So I'm going to put my answer, 7, so 12.6 volts is what that battery voltage needs to be to 3 sig figs in order for that ammeter to read 2 amps. So we needed the junction law and then 2 loop equations. Now when you're setting up your equations, if you wrote your equations in terms of IR without taking the delta V symbolic step, that is fine. Part of the reason I'm leaving it as delta V is I do see students sometimes just add resistors to voltages without really thinking about what they're doing. So I'm just trying to make it obvious that I'm adding voltages, potential differences, before plugging in any I's and R's and whatnot. But you certainly can jump to I times R, that sort of thing. Okay, anytime you see a circuit that has more than one battery, you will need to use the junction law and loop laws in order to solve the problems. If there's only one battery, you can go back to finding equivalent resistance. There's no problem with that. It's just when we have the multiple batteries.